10.5. I want to go over basically the same review we did the other day. What type of an angle is that? It's a central angle. Royal, what's the relationship between the angle and the arc? They're equal. Good. Jacob, what type of angle is this? That would be an inscribed angle. And Seth, what's the relationship between the angle and the arc?
The arc is twice the size of the angle measure.
The arc is twice the angle, or the angle's half the arc. Good. Everybody getting situated? Okay. What about if I have this scenario? Okay, so I have a tangent and a chord. What is the relationship, Carson, of the angle and the arc in this one? Jacob? The angle is still half the arc. So any time that my vertex is on the circle, what is our relationship? The angle is half the arc. AB. The angle is always half the arc if our vertex is on the circle. That's from last lesson. Okay. Also from last lesson, if I have angle 1 and arc A and arc B, I don't have anything for you today. Thanks, Braden. What is the relationship or an equation that I can set up here? Somebody who hasn't answered for me. Travis? Okay, I'm going to write it a little bit differently like we did on our theorem, but yes, you're right. Okay, so angle 1, according to our theorem exactly, angle 1 is half of arc A plus arc B, which is the same thing you said, right? Yeah, you just did it in a different order, which is fine. Okay, is there any scenario where my angle is ever on this side? Or are these always arcs? Your angle's still over here. Okay? These are always arcs. These will never be angles. So kind of to what Jacob just said, maybe they give me some of these things. They tell me that this is 18 degrees, this is 80 degrees, and this is X. Does that change where my angle goes? No, my angle is still here. Still 1/2. Arc A is now, Gavin, you're number 9 now. Yep. X. And arc B is now 80. Okay, there's still angle by itself, and the two arcs are together, correct? Is everybody with me today? Okay. Angle, arc, arc. Does it matter which order these go in? No. Why? Because we're adding them. Good. Okay. Last review from yesterday. I have two secants. Carly, do you remember our relationship here? Can you set that equation up for us, please? Good. So basically the same thing. Taylor Hart, what's different though? It's subtracting this time because I'm intersecting outside. Does it matter what order my arcs are in this time? Yes. Okay, because if they're in the wrong order, I end up getting a negative number, which we can't have for an angle, right? Okay. So when working on all of those problems, we were working with angles and arcs, right? Angles and arcs. What's the title of today's section? Are we working with angles and arcs anymore? No. Okay, so get your notes. We're on 10.5, segment lengths in circles. You are going to need your theorem sheets. You got your pink sheet? Yep. Thank you. We have 3 today. Yep. Okay. Now, notice none of, for sure the first one, but actually none of our 3 theorems are going to have names. So let's just make a category here, segment lengths in circles on our theorem sheet. And then we'll just number our theorems 1, 2, and 3. Because we don't need to know names anymore because we're not using our proofs. On these ones, we're not going to write down the whole paragraph because the words are a little bit confusing. So we're going to use our diagrams more. But pay attention as I read through this paragraph, and we'll see what we can pick up out of the words. Okay? The theorem says that if 2 chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Okay, so see why that's kind of confusing, right? Okay, what do we have? What does it tell us we have? We have 2 chords in a circle. Everybody agree with that? Okay. So I have 1 chord, 2 chords. Let's go ahead and put those as chords A, B, and C, D with our center point of E. And then moving on through the theorem, it says then the product. What does the word product mean? Multiply. So we're definitely multiplying. But we're multiplying the lengths of the segments of one chord. What segments, Matthias, make up chord AB? AE and EB. Okay, so we are multiplying AE times EB. And when we do that, our theorem goes on to tell us that is equal to what? What's the next thing it tells us? The products of the lengths of the segments of the other chord, which Travis would be what? But what would the lengths of the second chord be? What segments? ED times EC. Oh, you could do DE and CE. Yeah, because it's still the same segment, right? Yep. Okay, so when I have 2 chords, I have to multiply their segments together. Okay, we have had a little confusion mostly yesterday. Does that mean that the chords are congruent to each other or that they are the same length? That's where we've kind of been split. We've been split 50-50 all day. Is it yes or is it no? Okay, let's put some numbers in here, okay? So let's say that this DE is 10 and EC is 5. Okay? So I know that on one side I'm going to have 10 times 5, correct? On the other side, let's say this is 25, which would make this 2. Okay, I'm going to make them so they multiply to the same thing. These both equal what? 50. Okay? So when I multiply them together, I get my products. My products are equal. Right? Okay? Does that mean they're the same length? Now, how would I find the length of DC? I would add them. So I would have 10 plus 5, and the other one would be 25 plus 2. 10 plus 5 is, 25 plus 2 is. So does that mean they're the same length? No. Okay, so don't get confused. Just because they're telling us that our products are equal, does that mean our segments are congruent to each other? No. And I know that part's kind of confusing. Oops. Okay. But just because our products are equal does not mean the lengths are equal. Taylor?
So then multiplying them is just figuring out the third and center or something?
Not necessarily in the center. This is a theorem that's going to work. What we're going to use this for is we're going to be able to find missing lengths. Okay? It doesn't have to be in the center. Those don't have to be. That does not have to be the center point. Okay? So are those segments equal to each other? No, but their products are equal. Okay? So let's take a look at one example. This is probably going to be it has been so far for most students, the easier theorem of the day. Okay, so I think you'll pick up on this example pretty quickly. So I have my two chords. I have X, 9, 12, and, oops, I did that backwards, 18 and 12. I'm not going to put any letters in there because it doesn't necessarily matter for what we're looking for. This is an example. In your notes, please. Think you can set this up for us, Jacob? Yeah. Okay, give it a shot. Does anybody disagree with what we have there? Okay. I took my segment times my segment to make one chord, and 12 times 9, which were my two segments, to make my other chord. What do I get here, Vincent? What's 18 times x? At 18x. And 12 times 9? 108. What do I do now? Divide by 18. X equals 6. Okay. Again, you guys can do all the algebra skills. Okay, I know that. I've seen that. It's getting the problem set up properly. Okay, so do you have another theorem where your diagram looks like this? Yeah, from our last lesson, right? How are you going to know to use this theorem and not the lesson from 12.4? Or excuse me, 10.4, Royal? Right. Do we have any angles or arcs here? I mean, we have them, but we don't know any measures, right? Okay, so just understand what you're looking for. Here, we have segment lengths. So it's not going to make any sense to use our arcs and angles. So just understand what we're looking for and where your variable is actually at. Yeah, Amanda?
So since they're not congruent, that means that we can't just add the two and then...
Right. You're not adding anything here. Okay, it's to use the word product. It's all multiplication here. Okay? If you add them, they have no relationship being added. If you multiply them, then they're equal to each other. Okay? All right. Before we do our last two theorems, we got to clear a few terms up that they're going to use. We're not necessarily going to use this terminology a lot, but they're going to use them in our theorems. So to us, what is this segment called? That's a secant, right? Because it's a line that goes through the circle. What is this segment called? A tangent. Okay, we all agree on those, right? Now, they're going to change this because by definition, a secant is a line. You guys remember when we wrote the definitions down? It was a line. So it actually continues on, right? And it continues on this side. So what they're doing in these theorems, they are calling this a secant segment. Because it's only part of the whole secant, right? They've never called it a secant segment, though. They've called it... Because we haven't necessarily been talking about when it stops here and stops here. Now we're going to talk about, in this next theorem, we're going to talk about when we're going to break this up into a few different parts. Okay? How many parts does this secant segment have, Carson? You see multiple parts here? Yeah, this is your secant segment. Can I break it up into smaller pieces? Into how many? Two. This one and this one, right? That's why they broke it up for us. So they're going to call the whole thing a secant segment. Where is this part located at? On the outside. What's another word for that? Starts with an E. External, or in the exterior, right? This one would be in the interior. Okay, so in our next theorem, they're going to use the words secant segment, which would be this whole thing, and then they're going to use the word external secant segment, which would just be the blue. Okay. Again, we aren't necessarily going to use the terminology a whole bunch, but we're going to have to understand what they're talking about in our theorem. So the whole secant segment is just called a secant segment. This part is called the external secant segment. Moving on to what we called a tangent by definition is actually a line also. So what would we call just part of that tangent? A tangent segment. Good. Alright, we okay with those few terms? It's kind of the same thing we've been talking about, and I think you guys would have understood it even if I hadn't talked about it. If I'd have said secant segment or tangent segment, you probably would have just assumed what I was talking about. But this would have been the tricky part. External secant segment. We're going to use that. Okay. Questions on any of those three? Alright. Our second theorem is actually our longest theorem as far as the words on it go. It's going to also be a little bit confusing, so we'll read through it, see what we can pick out. If two secant segments share the same endpoint outside a circle, then the product of the length of one secant segment and the length of its external segment equals the product of the length of the other secant segment and the length of its external segment. A lot of stuff going on there again, right? Okay. But to draw the diagram, I know I have a circle with what? I have two secant segments. Okay, so we're going to start there. So I have my two secant segments. Put my letters in here. In my equation, the first part tells me, it says the product, which means we're multiplying again. So the product of the secant segment, which what would a secant segment be? AC would be one of them. Okay, so I have AC times, and then it says, and its external segment. Right, AB would be its external segment. So it's the whole thing times just the outside, right? And that's going to be tricky, so make sure we think about the whole secant segment times just the exterior. And then it says that that is equal to the other secant segment, which is AE times its external segment, AD. Good. Now when we write it like that, it seems a little bit easy. But it's going to be a little bit more difficult when I start to put numbers in for you guys. Okay, when you get to your assignment, it's going to be a little bit more challenging. Okay, so you have to make sure you're always taking the whole thing times just the outside, right? Okay, so if I go ahead and put some numbers in here, let's go 3 and 8. What goes here for AE? 11. Because it's 3 and 11, right? And I add those to get that whole length. So I have 11 times 3. Everybody okay there? You have to be careful though, because we're going to get to a problem. Okay, I'll set it up. We won't have any of this, and we're going to have a couple numbers. And even if you don't say it, some of us are going to think 3 times 8. Okay, so you just have to be very careful here. Make sure you're actually getting that whole segment. What if I did this? I left that as a 3, but then I did this. Because the book's going to give you this sometimes. How do I find AE, Royal?
Well, AB times AC equals 3 times.
Okay, so you're telling me that the whole length of AE is what? X. And the whole length of AD is 3. How did he know that X was the whole thing? Because the bar spans from A all the way to E. Okay, so did they give you the whole length that time? Yeah, they did. They told you it was from here to here. No, they didn't give you a number, right? But they did tell you it was X. Okay, so be careful. Sometimes they're going to label it like this. Sometimes they're going to label it like that. You just have to be careful. Make sure it's always the whole thing times the external. We okay there? We're going to do one more theorem, and then we'll do a couple examples using that. Theorem number 3. Last theorem for today. Again, see what we can pick out of this sentence. If a secant segment and a tangent segment share an endpoint outside a circle, then the product of the length of the secant segment and the length of its external segment equals the square of the length of the tangent segment. So do I have 2 secant segments still? I have a secant segment and a tangent segment. So I have a secant segment and a tangent segment. We got our letters on here. And then it tells us for our equation, the product, so we're doing what? Multiplying, of the length of the secant segment. What's the secant segment? AC. Right, Tamaya? Okay. Just want to make sure we're good. Okay, so the secant segment is AC times its external segment, which is AB, to that point it looks a lot like our last theorem, right? So anytime you have a secant segment, you're always doing the same thing. Okay? You're always taking the whole thing times the outside. Okay? And that should equal the square of the tangent segment. AD squared. I have had a little confusion. That doesn't mean square root, does it? No. It would have said square root. But it just says the square. So we just take that segment and square it. Okay. So you should have those 3 theorems on your theorem sheet. Use those on your assignment. Okay, we have 3 examples here. We probably won't have time for much of an assignment. We'll have a few problems, but we'll get through the lesson today and then we'll work on an assignment tomorrow. Close to example 2, mine's going to be a little bit different than what you have in your book. I'm going to do a different one so you have extra examples. Okay, so I have 2 secant segments. And my lengths are 10, 11, 12, and x. Tamaya, do you think you can set this up for us? Can you try?
No.
Why'd you get 21? You're right. I just want to know why.
I have a
10 and 11, because you need the whole thing, right? So 10 plus 11 gave her 21 times 11, which is just the external segment. This is where it's tricky. Good job. Because, one second, sorry. Those added together are 12 plus x, right? I have had some confusion. It's not 12x. What would that be doing? That would be multiplying. We got to add those and then multiply it by 12. Good. Let's scoot this over real quick. Okay. And from here, it's using our algebra skills. Okay. The hard part's setting it up. We start using our algebra skills. 121 times 11, or excuse me, 21 times 11. 231. What do I have to do here, Taylor Hart? Distribute. Good. So 12 times 12 is 144 plus 12x. Oops, not just 12. Matthias, keep going for me.
144 231 minus 144.
Okay, so we subtract 144. 231 minus 144 is 87. Good. Equals 12x. Laney? Divide by 12. Now this is where some of us might have to reach back and remember a couple things. Do I write that as a decimal? No, so what do I leave my answer as? 87/12. Is that an okay answer to have as an improper fraction? Yeah. Now, if this were an odd and you checked your answer in the back of the book, they're probably not going to have the improper fraction, right? They're going to have a decimal. How do you check and make sure you got the right answer? You just divide it and make sure your decimal's right. Okay? Pardon? If you could reduce it, you can. I don't think it's divisible by 3, though. Is it? Oh, well then, yeah, we need to reduce that. X equals 29 over 4. Thanks, Tamaya. I missed that. Okay? So yes, you would reduce that if possible. Yeah.
There's like a line over like the whole thing, X is just like the whole line. You know what I'm saying?
No.
Yeah.
Oh, like it's repeating?
Well, secant is X.
Oh, yeah.
But you have like, on that one where you had 3.
Okay, so like if I had this whole length drawn like that,
Yeah, there's X.
and this was X,
Yeah, would you subtract that by 12?
you won't have to, because you want the whole thing times the outside. Well, the whole thing is X, and the outside is 12. So they made it easier for you, actually.
Oh, okay.
Okay? Alright. Next example, I can't remember what example it is. You guys remember that example we did a week or two ago where we had the water tower and we found the radius of it without actually getting inside the water tower and measuring it? You guys remember that? Most of us? Yeah, it wasn't too long ago. It's a little longer than that.
Oh, that was the mountain.
Yeah, we did the mountain one 2 days ago. Hey, so what we have here is very similar, except here they tell us we have a shark tank, an aquarium, which obviously you don't want to get inside of and measure. Hey, they want us to find the radius. How many radius do you see here? 2. 1 there and 1 there, right? Okay. And then they tell us that we are standing 8 feet from the tank, and to the point of tangency is 20 feet. Should we be able to find the radius of this aquarium without actually getting inside the aquarium? Yeah. Okay. Now you got to be careful here. You gonna set it up for us, Jacob? Okay. Before you set it up, I'll let you set it up. But I want to ask you guys one question. Can I change this whole length to something else? There's 2 choices. What did you say, Taylor? Well, we want to find the radius, so I don't want to put it as x. Not r squared. I could write it as 2r. I also had some people write it as d. Why? Because that's the diameter, right? Now your only problem here, if you write it as d and you solve this all the way down, you get d equals blank, right? But what did they ask for? The radius. So then you'd have to do what to your answer? Divide by 2. So I would like to go Carson's way personally and say that that's 2r, because then when I get done, I get r equals, and I'm just done, right? Okay, so that's up to you. You just have to understand where you're going with it. Now, Jacob, I'll let you go ahead and set this up for us. Am I, to find a length, do I add or multiply for segment addition? I do what? Segment addition? I add. So the whole length is, not quite. You can't combine those because they're not like terms. So it's, there you go, 8 plus 2r. So that's my whole length times 8. Good. Good. You get why you can't add those, right? That's like a 2x and an 8. Not like terms. Okay. So Amanda, what do I get out of this? I do.
So it would be 64.
There you go, 64
Plus 16.
plus 16r. Anybody know that? 400. Okay, what to mine? Go for it. Subtract 64. Again, I don't think you guys struggle once we get to the algebra skills. So I have 16r equals 336. Divide by 16. R equals 21. Did I go too fast there at the end? What's my label? Feet. Okay. I know I went a little quick there with the algebra, but we can do the algebra, right? I've seen you guys do the algebra. I know you can do that. Setting it up properly is the challenge. Okay, we've had a lot of theorems and a lot of different equations through the course of the year. You got to make sure you use the right one. Okay. Guys ready for the last challenge? Okay. One more challenge for us here. I have basically the same diagram. This is 11, this is 9, this is x. So I'm still using the same theorem, right? You want to set it up, Royal? Okay, go for it. Yeah, you might get an x squared, right? Because then you'd square it. I get what you're saying. So like up here, if that was our variable, yeah, you'd have a number over here equals x squared, right? How do you undo x squared? Square root. So you would end up with a radical. That's possible. We can reduce a radical though, right? Okay. So yeah, there's a possibility that you might have to square root something, depending on where your x is located at. And this is actually a pretty good example of that. Set this up for me, please, Seth. X plus 9 times x equals 11 squared. Everybody good there? Okay. Ryan, when I multiply this, I distribute, correct? What is x times x? That's x plus x. There you go. X squared plus 9x. Good. Carly, do you see a problem with this? What's our problem? Right, I can't, because I have two different variables, don't I? Okay? When you end up with two variables, x squared and x, we're going to have to use our quadratic formula. Okay? Get this written down in your notes. You're going to need that. Okay? Quadratic formula. I do know that you guys used that last year. Okay? I actually think they're learning it right now in Algebra 1. Your quadratic formula is negative b plus or minus the square root of b squared minus 4ac. All over 2a. Okay. Now we do have to be very careful. A is where? In front of x squared. That's where I'm going. Give me a second. It's in front of x squared, right? Hey, b is where? In front of x. Okay? For you to be able to use the quadratic formula, your equation has to be in this exact form. So everything needs to be on one side, and it needs to be equal to 0 every single time, or this formula does not work. So, do I have this in the proper form that I need? No. What do I need to do, Tamaya? Subtract 121. So when I do that, x squared plus 9x minus 121 equals 0. Now do I have it in the form I need? Yes. So I can start plugging it into that. Okay, so that's what we're going to look at. Negative b. b is in front of my x, right? So it's negative 9 plus or minus the square root of b squared. b is 9. So I have 9 squared. I'm going to write every little step out this first time. Minus 4 times a. What is a? What's in front of x squared? 1. And c is, this one's tricky, it's what? Negative 121. We don't want our variables. We're trying to figure out what does x equal. Okay, so we're not writing this with any variables because then we're still going to have the same problem that we started with. All divided by 2 times 1. Okay. Use your algebra here. Start simplifying this. Negative 9 plus or minus, what's 9 squared? 81. Minus, what is 4 times 1 times negative 121? It's 484. You can use your calculator on that, but it's negative, right? And then 2 negatives make a positive. over 2. Okay. Negative 9 plus or minus, what do I get on the inside? 565 divided by 2. Okay. If this radical was reducible, what would you do with it? If it was a perfect square, you'd square root it. If you could reduce this radical, would you reduce it?
Yes.
By taking out perfect squares? Okay. This one's not reducible. Okay. We'll work on some more tomorrow that are. Okay. So this is as far as I want you to go with this. I don't want you to change this into a decimal. Okay. I want you to leave it as an exact answer. Okay. That's basically exactly what you're going to have to do with quadratic formula next year in Algebra 2 also. You're going to have to be able to come up with an answer that looks like this. Okay. Now, when I have a number here, it can't be what?
0. Negative.
It can't be negative. Can you have a negative length? No. So what you'll have to do, and again, we'll do more tomorrow, check this. One of these ways, plus or minus, guys, stay with me here. We're almost done. Plus or minus might give you a negative answer. Is that an option for your x? No. Okay, so just be aware of that. Think about that for when we look at some more tomorrow. I do have 3 problems I want you to try for tomorrow. We'll come back to this and touch some more on all of this tomorrow. Okay, remember here, when you have a secant, do you use the inside by itself ever? No, it's always the whole thing times the outside. Okay, so I'm going to have you do 6 problems for me tomorrow. Most of them will deal with those theorems. On page 632, give 3 through 8 a try. Yep, we'll look at those 6 problems tomorrow in class, and I have one more example for you tomorrow also. And then we'll work on the assignment the rest of class period tomorrow.